He kōna I purangi tēnei nā te reo irirangi o Aotearoa.
This is not your usual Tuesday in Mosgiel. Laid out on plastic pallets in a concreted space that normally serves as an area for livestock postmortems is a 5-metre-long beaked whale. Clad in gumboots, overalls and plastic gloves, a large team of excited people are peeling back the whale's blubber, exposing the dark red muscles below. Each step revealing a new secret of this, the rarest whale, or tohura, in the world. Kia ora, nau mai haramai ki te ao hurihanga. Hello and welcome to Our Changing World. Ko Concannon tēnei.
It's been really exciting. I'm a massive nerd about what I do, and to find other people who are, massively nerdy about what they do too. It's like, even though that's not my thing, I just really relate to that.
This is Rachel Wesley from Te Runanga o Ōtako. Or in the Ngaitahu mita, or dialect, where K replaces NG, runaka.
I've been describing myself as head runaka wrangler.
We're chatting midway through the week-long dissection, which took place early December 2024 at the Invermay Ag Research Facilities in Mosgiel, 20 minutes south of Ōtepoti, Dunedin. But Rachel has been involved from the early days, shortly after this spade-toothed whale called Onumia was found. It was named after the Te Reo Māori name for the stretch of coastline it was found on, in the rohe of Ngaitahu.
Onumia washed up right on the foreshore of Taiari Block B, which is one of the native reserves that were withheld from the Otago sale back in 1844. So it's pretty significant for us. And Onumia acts as a reconnection, to our reo, to our whenua, and to the moana and this tohura in particular.
There's a large team involved in this dissection effort. New Zealand and international whale scientists, local runanga members and rangatahi Māori, doc experts, Māori whale tohunga, University of Otago scientists, and staff from Tuhura Otago Museum. And between July, when the whale first washed up and was spotted on a webcam, to this December dissection week, there's been a lot to sort out.
Discussions with DOC and Tuhura Otago Museum around whether we would dissect the whale or not, and then what sort of expectations the runaka had around how that would take place and our role.
But now the team is in place and the plan has been decided. The whale, which had been stored frozen, is gently defrosting as the week kicks off with a Monday morning media stand-up.
I can't tell you how extraordinary it is for me personally. I mean, it's a wonderful thing, but for me personally, it's unbelievable.
This is Anton van Helden, a senior science advisor in the marine species team at the Department of Conservation. And in a room full of people super excited to learn more about this whale, Anton might just edge out the title of most excited.
I was sitting at home on my couch recovering from surgery, and I get a text message with an image on it, and I go, oh my goodness, it's a spade-toothed whale.
For many years now, Anton has been one of very few experts with direct knowledge of this super rare whale. He helped give it its common name, the spade-toothed whale, to distinguish it from its cousin, the strap-toothed whale. The spade in this case refers to a tool from whaling days, the shape of which is similar to the single tusk tooth that males have coming from their lower jaw. And before 2010, the shape of these teeth was one thing amongst very little that we knew about this whale species. All that had ever been found was one jawbone and 2 partial skulls. Then in 2010, 2 partial whale bodies, a mother and a calf, washed up in the Bay of Plenty. They were originally misidentified as a more common beaked whale and buried. But tissue samples later confirmed their spade-toothedness by DNA analysis. In 2017, another partial body washed up, north of Gisborne. Again, first mistaken and buried before later being identified. Incomplete skeletons from both these strandings have been exhumed and are now housed in Te Papa. But this is the first freshly stranded complete whale, and only the 7th record of this species, all but one of which are from Aotearoa, New Zealand.
Of the 24 species of beaked whale known worldwide, we have 13 of those species here in New Zealand. And of those, 7 of those species were first described from specimens from New Zealand. So this is a key hotspot. It's a key part of the global jigsaw puzzle for understanding these animals.
To picture a beaked whale, you might be best to start from a dolphin. Their beak, what scientists call their rostrum, is the pointed nose bit like a dolphin's. The body shape is similar-ish, but chunkier, less streamlined, with a small dorsal fin and a noticeable bulge at the top of their head. And they've evolved to be champion deep divers.
Beaked whales hold the record as breath-hold diving mammals. So a goose-beaked whale holds the record. It managed to stay submerged, hold its breath if you like, for 222 minutes and to dive to a depth of 2,998 metres.
222 minutes is 3 hours and 42 minutes. This is a mammal that needs to breathe air like you and I. But they are so amazingly adapted to the long, deep diving life that they live, it's estimated that beaked whales spend as little as 8% of their lives at the surface, which is why they remain so elusive. These results came from satellite tagging studies, which have shown that a kind of regular dive for those species of whales is about an hour. For spade-toothed whales specifically, we just don't know. But they'll be using some of the same physiological tricks to cope with the pressurized environment of the ocean depths.
As we go deeper, the amount of air that you have gets more and more and more constrained by pressure. And so these guys, when they dive, they collapse their lungs. So oxygen in their bodies is contained more in the muscles than it is in the lungs itself for activities. So when you look at the muscles on these guys, they're dark red, and that's because they contain a lot of myoglobin, which is the equivalent of the hemoglobin that we have in our blood to transport oxygen around the body.
Media stand-up complete, the team kicks into gear, taking whole animal measurements and heaps of photographs before they begin to remove the thick layer of blubber. When I arrive on Tuesday, work is underway on identifying some of the muscles below. Behind the head, near the flipper, Professor Joy Reidenberg, who's flown in from New York, is slicing off an outer muscle, which is kind of like a big sock, she says, that controls the shape of the skin of the whale.
But underneath it, these muscles here are attached to the flipper. So the flipper has a shoulder blade, which is embedded in the body wall here. And coming from that shoulder blade are some of the same muscles that you and I have. One of them is a muscle that goes down to, in us, the small of our back. That's called latissimus dorsi, whose name literally means the muscle on the back with the most latitude. It's the widest muscle. But that's not the case for these animals. They don't use their upper extremity or flippers in the same way we do. So that muscle's not that big. And so we were looking for it to establish where it goes, and this looks like it may be it. This band I'm looking at right here. I think that's it. And I think yes, we do. We're going to pull that out. I got to see a little more shoulder blade to know. But I feel the shoulder blade. Here's the shoulder blade. It's right here. Yeah. Yep. I think once we get this off, we're going to have a nice view of all those back muscles around the shoulder blade and get an idea of how they control the movement of that flipper, which is pretty cool because it looks like they tuck it in real tight when they're diving deep. So they kind of look like a torpedo just going straight down because the flipper falls into a little pocket and doesn't stick out and cause friction. But if they need it to just change slightly the direction they're going, they'll put that flipper out like a little fin on a rocket and help steer it back and forth.
Further down the body are Sophie White, paleontology lab manager at the University of Otago, and Takauri Nui Parata. With large, sharp knives in hand, Sophie and Takauri Nui are carving into a big body of muscle, with each semi-frozen chunk taken aside to be weighed.
It's really frozen on the inside, so it's going to keep the organs really cool, but it's just tricky to cut into because it's really thick.
Yeah, you can see all these fibers.
Yeah, you can see all the fibers. So this really dark red, kind of purpley, all of that is the muscle.
Yep. Next thing. Alright.
So there's a lot of myoglobin in it, and it's the most of our deep diving species have this really, really dark, almost kind of black meat. So it's really characteristic for these guys.
Cody, you've come down from Te Ika Maui? From Whangarei. All the way down.
They gave us the call to come and help with the mahi.
And so you've been involved in other whale strandings and investigations up north?
Yeah, particularly with our own rohe within Ngāti Wai, and been lucky enough to be asked to come and help other iwi as well.
Te Kauri Nui has learned from and travelled down with his father, Hori Parata, a Ngāti Wai tohunga or Māori expert in whale recovery. They're here to share their traditional mātauranga, or knowledge. You can hear that it's a loud and busy room, with lots of people working away at the same time. At the head of the whale, I meet Dr. Carolyn Locke from the University of Otago Faculty of Dentistry.
And I'm a whale and dolphin researcher as well. I'm interested in the evolution and structure of their teeth. What is interesting about big whales in general, they have over evolution of 1 million of years reduced the number of teeth they have. So they have just one pair of really big tusks that erupt in males. They are unerupted in females. And this specimen in particular, the tusks are broken. And what is interesting, it seems that it was broken before the animal died. So tomorrow we're going to scan them and try to understand what happened, what type of impact has caused this, and the consequences for the health of the animal. So I'm actually bringing a dental CT scanner that's used in patients. It's going to be a very different patient this time, but we're going to 3D scan the surface and then create a model so we can understand a bit of the shape and what has happened for that fracture to happen.
These whales aren't using their teeth like you or I would to chew things. They use them more like a deer uses their antlers, to flex on other male whales. But an interesting new tooth finding did come out of this week's work. Later, the team reported finding tiny vestigial teeth in the upper jaw of this whale, a link back to a time when they had more teeth, as Caroline mentioned. The work continues, using string to mark and identify the muscles around the flipper and head, and taking the large back muscles away to start to reveal the organs below. Having kept it intact so far, the whale's head is then removed, and on Thursday driven the short trip to the on-site CT scanner. Wrapped in clear plastic, it's wheeled in on a trolley and then manoeuvred into position in the mouth of the scanner. Once it's in place, we shuffle into the side room where the computer sits, behind a clear glass window looking out at the scanner. Ag Research's Dr. Neville Jobson is at the controls.
Lung, detail, soft, edge, bone, and bone plus.
And so what you're doing here, Neville, is setting up different kind of scan parameters to look for different things?
Correct. So the first one we just use is for simply locations. So where do we start, where do we end, is everything in the field of view. And then the second one is we're doing one scan that will capture all the X-ray information, and then we're reconstructing it with different settings so that it gives good contrast between different tissues so that you'll be able to see a range of different things.
So one scan, so one source of information, but then it uses the information in a slightly different way.
That's right. It takes all of that information, the X-ray dose as it's gone through and done it, and then it has software that reconstructs it in different ways so that we can see really good detail in the lungs, or really good contrast between soft tissues, or really sharp edges to bones if we're trying to look at that sort of thing. So we'll do all of those reconstructions and generate probably tens of thousands of images for poor Michael to go through.
Poor Michael here refers to Dr. Michael Denk of Woods Hole Oceanographic Institute in Massachusetts. But I'd save your pity. Michael is almost vibrating with excitement, his eyes glued to the screen.
That is the beauty of this technology. By means of using these different methods and processing of the scans, you can look at all the various types of tissues in these animals that make up their architecture and visualize them, as full as you can, to get the big picture in these massive and incredibly complex animals.
So Neville, in terms of your day-to-day, what are you normally looking at through the CT scanner?
We normally are looking at farm animals, so sheep and deer, and we're looking at how much meat and fat that they would have in different regions of their body, size of their rumens for greenhouse gas research, anything where we might want to measure internally something in the animal. 20 years ago, we would have to kill animals in order to measure those things, so the CT scanner lets us measure them longitudinally. We can measure it today, we can apply a treatment, and in 2 weeks we can measure them again and see whether our treatments change anything. So we can follow a lamb growing in a uterus of a sheep, or measure young rams for how much meat they might produce for a farmer.
Is this the first time that you have looked at a marine mammal in this CT scanner?
No, we have scanned a porpoise and another small whale, but I can't remember the species. It was about 10 years ago. Yeah, so there's all sorts of weird and wonderful things that go through, and they're quite fun days, to do, because they're very different to the other things that we see.
With everything set up, it's showtime. The group is now kind of huddled around the computer screen as Neville presses start.
It'll scan and reconstruct that first, the standard, and then successively it will just go through and do the reconstruction, so we can just watch that as it happens. So the actual scanning is disappointingly short. It's going to take 88 seconds, and here it is generating it as we go.
It's sort of creeping through the tip of the rostrum.
There we go.
Little bead, yes.
Yeah.
You can actually see the teeth coming out of the jaw. So now we're getting to a bigger depth of tissue, and so you're just getting in this. We'll just have to see what the different algorithms are like in terms of that graininess.
While there are some initial things that are obvious, the bone structure and the fatty area on the top of the head called the melon, which is involved in helping the whale focus sound and is what Michael is particularly interested in, there are other things that will take the researchers a lot of image processing and time to figure out. Dr. Alex Worth, who has flown in from Virginia, is particularly interested in the shape of the mouth and tongue. Because, with just one tooth per jaw, these whales are not using them to catch and chew prey. Instead, they're suction feeders.
They have a really powerful piston-like tongue that creates lower than ambient pressure, that is to say less than the water around, just by expanding a space. And then the water just naturally flows in really, really quickly. And they can do this very, very forcefully and very strongly.
What are they feeding on? Do we know?
The vast majority of suction-feeding whales are feeding on squid or large fish, but occasionally they feed on smaller items, and we know they're doing this in many ways. One is that we can find items in their stomach that are completely intact and undisturbed, including very delicate shrimp that have no bite marks, no tooth marks or puncture marks, and you wonder, how did this get in the whale's stomach without it using its teeth at all? We also find non-prey items. There are sand dollars, pieces of coral, small rocks. In the biggest whales, like sperm whales, you find large rocks in their stomach.
And what are you hoping to find out from the CT images that have been captured?
My specialty working on whale tongues, I'm very interested in how the tongue is attached to the jaws, to the throat, to the chin, as well as to the larynx, the voice box that produces sound. So when the whale does move its piston-like tongue for feeding, that has implications or ramifications for how it makes sound, how it breathes. Everything in the head is all connected together. So the CT scan will help us to better visualize, even before we dissect it, even before we cut it apart, exactly all the connections and relations of all those tissues, the muscle, the bone, the cartilage within the skull.
Alex has also got an interest in Anton and Michael's key questions around how the whales make, focus, and use sound. Because remember, they're diving very deep for long periods of time, but they need air to make sound.
These whales are making sounds by passing air through tiny little valve-like structures. It's very much like if you can imagine having a balloon that you inflate with air, but instead of tying it off, you just relax the opening of that balloon, and you've probably done this. You can hear it make funny sounds, squeaking, because those tissues are vibrating. That's how whales make sound. They have the equivalent of lips, like we have in the front of our mouth, within their head, but it's actually just a tiny, tiny amount of air that they use to make those sound pulses. They don't have diving issues when they go down deep like scuba divers do that have to rise very slowly because they're not continually breathing as human divers do. They take a single breath down, or in some cases they even exhale before they go down, and then their lungs collapse at great depth, but all the air that was in their lungs and in their trachea, that's just enough to give them the sound pulses that they need to find their food, which of course they need because they're in the pitch black inky depths of the sea.
When we return to the main site, there's a break in activity, with people grabbing some lunch. While the scanning has been going on, some of the organs have been removed for weighing and measuring. Rachel Wesley points out one of the whale's huge lungs, sitting out on a metal tray.
The lungs was an armful, both arms holding the lung, cradling it, and the heart and the major vessels coming out of there was a two-person job. So I don't know if that gives a good scale of the size of what we were dealing with this morning.
They've discovered that this strap-toothed whale has 9 stomachs. Each beaked whale seems to have a unique stomach plan, so they didn't know what to expect. And they found some leftovers inside. Some squid beaks and squid eye lenses, along with some parasites, which were handed off to parasitologists at the University of Otago to identify. There were also tissue samples taken to look for contaminants, something the Rinanga requested.
And that's hugely beneficial for us as we have quite a large, rohe moana, marine area as well. And so what's going on out there in terms of contaminants or anything else that may be going on out in the moana affects a whole range of things for us. So this tohora can give us a really good glimpse into that wider sort of environmental space.
Now, this was a scientific dissection, not an autopsy. But the team did find bruising to the head and neck and a broken jaw, which has led them to believe that the whale suffered some sort of head trauma that may have been the cause of its death. What was dissected off has been buried again at the site where the whale was found. The skeleton is now in Littleton, in the care of Judith Street. 3 months in large bacteria-filled tanks has stripped the skeleton of meat. But the bones of deep-diving whales contain lots of oils, Judith tells me, and it will take a few years of treatment to get them all out. They will reassess in about 2 years' time. Once the skeleton is ready, it will return to Ōtepoti, Dunedin.
Then it will go to Tuhura, Otago Museum. We're developing an agreement with the museum, so we're gifting it, but we still expect that there will be some conditions around that gift just to make sure that the mauri and the wairuataka of Onumea is cared for and maintained within the museum.
But the jawbone, the kawai, will stay with the hapu.
Being able to claim the kawai, as mana whenua under our rakatirataka and in line with old practices from the past has been a huge step forward from what our hapu's been able to do in the past.
Eventually, years from now, the skeleton will go on display in the museum with a 3D printed version of the kawai. For Rachel and Te Runanga o Ōtako, this has been an opportunity for the next generation of their leaders to build back up the tribal knowledge of working with tohora. People like Tumai Cassidy.
Yeah, we have a long association with whales, right back through to when some of our ancestors came from Polynesia following those migration pathways of whales. According to our traditions, some of our ancestors arrived here on the backs of whales. And so not just, utilising the physical aspects of whales, actually utilising some of the knowledge that the whales hold around navigating the Pacific Ocean. But yeah, just like other cultures around the world, utilising the different parts, the oils, the fats, some of the bones, those kind of things, to give us an ability to live our lives on land. And so really it's about being able to show gratitude for the gift.
And for him, the experience has been one of a two-way street of knowledge sharing.
In terms of mahitahi working in collaboration with experts in the scientific world, you need to understand how they view things and what they want to, get out of this process. I mean, it's been really cool having experts of some of our Māori knowledge systems around whales. Hori Parata from Ngāti Wai has come down to just support our hapu and all the knowledge that he brings along with his son Kauri Nui. And all of the knowledge, when it's pulled together, it'll help our people to be able to respond. And if we have another whale that washes up, we'll have just more people locally that can sort of do it justice in following all of the different protocols under both knowledge systems.
Thanks to the members of the whale dissection team that I spoke to. Rachel Wesley, Anton van Helden, Takori Nui Parata, Sophie White, Dr. Carolyn Locke, Professor Joy Reidenberg, Dr. Michael Denk, Dr. Alex Worth, and to Mai Cassidy. Thanks also to Kane Fleury, Hori Parata, and Judith Street for background information. And thanks to my RNZ colleague Tess Brunton for the media stand-up audio. This episode was produced by me, Claire Concannon, with production help from Ellen Rikers and sound engineering by Phil Bench. We've got lots of details in the show notes for this episode. You can find them on the RNZ podcast page, or you can visit rnz.co.nz/OCW for a bit of a write-up and some photos from the dissection. Tēnā koe I whakarongo mai. Thank you so much for listening. I'm Claire Concannon. Have a great week. Kia pai, te wiki.